I had issues with my slides. I got ready, like in the old software that I usually use, I had everything all ready to go, and then like Saturday morning or something when I got up, nothing was working. So I ended up switching it to PowerPoint, so it'll look different today. And I'm not sure about if I'll keep using it or not. It was a lot of effort to put them together compared with the other ones. But they look really good. There's no question. They probably look a lot better. And I think you can see pretty well, I hope. Maybe a little bit low on the screen right here. But trigonometry, which maybe it's something you've dreaded getting to this because it's got to be the hardest thing. Not necessarily. I think I told you this joke before, but it's this little cartoon of two little kids like that are below the rail on the chalkboard, looking up on the chalkboard. It says 1 + 1 equals, and one of them turns to the other and goes, just what I always feared, calculus. It's like that unknown thing that's out there. It must be really tough. And to them, 1 + 1 is pretty abstract. They know what they're looking at. So anyways, trigonometry, the word means the measure of triangles. And since triangles are made up of 3 sides and 3 angles, it's mostly about the measures of the sides and angles in a triangle. Right? It originated in the 3rd century BC when astronomers noted the fixed ratios of the sides of similar right triangles. What are similar triangles? You did this before. They have the same angles, but maybe not the same side lengths, right? They could be they're proportional. I would say they're the same shape, but not necessarily the same size. So even in those days, they knew what similar triangles were, and they noticed that these ratios of sides, they're always the same thing. Now, in between the 3rd century and later on, I think it was used a lot for land measurement and things like that. Okay. Trigonometric functions are periodic, meaning they repeat themselves over and over again, right? They repeat themselves. Each cycle that it goes through is called one period. And if you look at the graph that I've got on the screen, that's actually the graph of y equals sine x. And you could tell that it kind of looks like a wave, right? And so if you wanted to model some kind of a real world process that is wave-like, then you kind of need a trig function. Do you have a question? Yes, infinitely. Because if they didn't repeat infinitely, let's say that it just went up and down like 10 times. Okay, well you could do that with an 11th degree polynomial, right? Because that could have 10 turning points in it. But these things go on forever. So they're used in many fields: physics, engineering, acoustics, meteorology. Just think, if you have to model temperature, and temperature goes up to a maximum every day, and then it goes to a minimum every night, and goes to a maximum the next day, and a minimum, and it's going to go on forever, right? You need a function that kind of behaves like that. How about the stock market? It goes up and it goes down, and it goes up and down. How about the waves in the ocean? What better to model waves with than a wave? In fact, the graph of the sine function is called a sine wave. And you can hear sine wave referenced, not just in math and science, but just in the newspaper. They may say something resembled a sine wave, and you're kind of supposed to know what that means. It just means it's like a wave. All right. So this first lesson is actually a review of what you did in geometry. Maybe there's a little more detail in it than what you did when you did it in geometry. And it's presented a little bit differently just because of the way this textbook does it a little bit. But I'm not really trying to accomplish much more than what I'm pretty sure that you already got in geometry. I was going to do the lessons a little out of order, which is normally the way we do this. But tomorrow during 1B, I'm being pulled from my 1B class to go to some SOL-related meeting as everybody prepares to pull their hair out over the SOLs. So they're going to watch the video that we're doing right now, and I didn't want to have it to be all new stuff. I wanted it to be somewhat things that they've already seen. So they're listening to me talk right now. Okay, so these are the objectives, yeah, I would expect that we're going to take our quiz on this short lesson, short unit on Friday, and then the test will be next Thursday. That's the plan, anyways. All right, so this is stuff, I'm pretty sure you had this pretty much just like this before, right? You start with a right triangle, you label one of the angles, right? In this case, the bottom left angle there has got a symbol in it. That's the Greek letter theta, right? And theta is by far the most common variable used when you're representing an angle. Right? Okay, with respect to the position of that angle, okay, then you can label the three sides of the triangle as being opposite, meaning it's across from the angle that's marked, adjacent, which means it's right next to the angle that's marked, or the hypotenuse. That's always the hypotenuse, right? Hypotenuse in a right triangle is across from the 90-degree angle, and that doesn't change no matter if I put the theta in this angle or if I put it in the top, it wouldn't change. Hypotenuse stays the same. Okay, so based on a triangle drawn like that, labeled like that, then we can define three trig functions: sine, cosine, and tangent, right? And that's the way you pronounce them. The sine of theta is defined as the ratio of the sides, opposite divided by hypotenuse, right? That's what those 3rd century astronomers saying. They noticed that the ratios of the sides were constant. The cosine of theta is the adjacent side divided by the hypotenuse, and the tangent is the opposite divided by the adjacent. Now, do you recognize SOHCAHTOA? Did you use that to remember, the definitions for sine, cosine, and tangent? Right, so sine, the SOH, sine equals opposite over hypotenuse. CAH, cosine equals adjacent over hypotenuse. TOA, tangent equals opposite over adjacent. Does anybody have any clever ways to remember those letters in that order? Or do you just pronounce it SOHCAHTOA and you know what it is? Did you ever hear of these? Some old horse caught a horse taking oats away. Kind of like PEMDAS, Or some old horse came a hoppin' through our alley. Those are two that kids taught me because I didn't use those when I was a kid. This is the one that I used when I was a kid. OAO H H H. Why's that giving me trouble? A. I'm really learning how to use this PowerPoint. But so we would say Oliver and olive oil have had algebra. And O over H was the opposite over hypotenuse. A over H, cosine, O over A, tangent. You just had to remember them in that order. But I wrote that down more times than I can remember. Had to remember sine, cosine, tangent. I would write it out and then figure it out from there. So whatever way you have to remember them, you definitely have to know how we define sine, cosine, and tangent. Okay. Now, what you probably didn't do then, that we add now, is that there's actually 6 trig functions, not just the sine, cosine, and tangent, but the reciprocal functions, which means that they are the reciprocals of the sine, cosine, and tangent. And they are called the cosecant, the secant, and the cotangent. And that's how they're pronounced. So the cosecant is the reciprocal of the sine. That's why I wrote them right across from each other. The secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent. Right? So cosecant is hypotenuse over opposite. Secant is opposite over adjacent. Oh, that is wrong. Sorry about that. Fix, on the fly. Nobody caught this before. Hypotenuse. Okay, now we got it. And then the cotangent is adjacent over opposite. So you got to remember all 6. We've got a way to remember the first 3, right? Sine, cosine, and tangent. How do you remember which of the reciprocal functions is the flip of which of the original three? I mean, the way I always remember it is cotangent is clearly the flip of the tangent. Now, if I was like just saying, if somebody just said, well, just guess, which one do you think would be the flip of the cosine, the cosecant or the secant? I would say probably the cosecant, right? Cosine, cosecant, and I would be wrong. So that's always the way I remember it. It's not what I would have thought. So that, you know, but one way or the other, you got to remember how it goes, how those all line up. Okay. Good, Michelle? Okay. So here's a typical problem that we do. Evaluate the 6 trigonometric functions of the angle theta in the triangle that's given right there. Okay, well, I see theta, and I see 2 of the sides labeled with measurements, but I'm missing the third side. How do you find the third side of a right triangle? There's also what you learned this in geometry. This was what you did before you got to the trigonometry part. Given 2 sides of a right triangle, how do you find the third side? Pythagorean theorem, right? So Pythagorean theorem would say that a squared plus b squared equals c squared. So we would say this side, this missing side, would be the square root of 5 squared plus 12 squared. Why is that goofing up? So that's the square root of 169, which is 13. 13. Okay, now that I've got everything labeled, right? Well, I could do this too if you want to make this. I could like let me label the 3 sides. This is the hypotenuse, obviously. This is the adjacent, and this is the opposite. Okay, now let's go through the sine is opposite over hypotenuse. So what will that be? 5 over 13. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. 5 over 12. Okay, now we got the 3 reciprocal functions. You know, when I have to fill these in, I always make sure I write the reciprocal, right across from the one it's the reciprocal of. So that once I've done these 3, I just have to flip them, right? 13 over 5, 13 over 12, and 12 over 5. Done. And what, you know, we've got theta in there. Do we know what theta is? No, you don't, right? It's an angle. We're going to learn by the end of the lesson. We'll know how to find theta. Yeah. No. We're never taking the sines, cosines of the right angle. Okay. So don't try to do that. I mean, we will find in the next lesson, we'll find the sine and the cosine of 90 degrees. They have an answer, but not something you can get from a right triangle. Okay. So we don't really know what the theta is. You know, a common mistake that I'll see when you have this kind of problem is that you're going to try to like take that 5 over 13 and put it in the place of the theta, like say sine of 5 over 13. That's not correct. Remember that the theta, or whatever it is you're going to call the angle, the sine, cosine, tangent, the argument is always an angle. It's not the ratio of sides that goes in the function, right? Always an angle goes in the function. So here's your U try, your first U try of the fourth 9 weeks. Right, so this side now, I mean, remember with Pythagorean theorem, if you're missing one of the legs of the right triangle, it's not an add anymore, it's a subtract, right? It's the square root of 17 squared minus 15 squared, which is 64. So the square root is 8. So then, now, make sure you're using that angle, as I call it the reference angle, but 15 over 17, 8 over 17, 15 over 8. Right? Okay, next. Okay, here's a slightly different kind of problem. It says if theta is an acute angle of a right triangle and the sine of theta is 4/7, what is the tangent of theta? Okay, first step, what do you think the first step is to solve this problem? Draw a picture, right? If you can do this out of picture, then you are better than me. So let me draw a triangle. Okay, see how I like how that does that. Okay, now I'm going to label an angle. Doesn't matter which, it's got to be one of the acute angles, so I'll label that one. And it says the sine is 4/7, but we know that that means the opposite, oh, why does that do that? That's opposite over hypotenuse, so it should be 4/7. Okay, now I've just got to use Pythagorean theorem, right? So this side here is going to be the square root of 49 minus 16, which is the square root of 33. Okay, and you just have to leave it. Can you simplify the square root of 33 without turning it into a decimal? No. It's not a perfect square. It doesn't have any factors that are perfect squares, so the square root of 33. Now we've got to answer the question, what is the tangent of theta? Let's see, the tangent of theta should be the opposite over the adjacent, right? So that is 4 divided by the square root of 33. But we don't generally leave a square root in the denominator. We have to rationalize the denominator. How do we rationalize that denominator? You multiply by the square root of 33 divided by the square root of 33. Right? Because that's 1. You just multiplied by 1. You're allowed to do that. But now the square root of 33 times the square root of 33 in the denominator is 33. No more radical. And in the numerator, you have 4 times the square root of 33. Why is it doing that? So we do have to rationalize denominators in a case like this. Don't just turn it into a decimal. Rationalize the denominator. Okay, so here's your U try, I'm sure. This is supposed to be your U try. U try. So the missing side was the square root of 51, right? Then the sign would be opposite over hypotenuse. Square root of 51 over 10. No need to rationalize. You're done. Okay. Okay, now we're going to combine this with something else that you learned in the same unit. After you learned Pythagorean theorem and before you did trigonometry, you did the two special right triangles, 45, 45, 90 and 30, 60, 90. Right? So if you didn't remember, the formulas for the side lengths are x and x for the two legs of a 45, 45, 90, meaning they're the same. And x times the square root of 2 is the hypotenuse. Now, do we know what the side lengths of any of those sides are? No, we don't. But remember, we don't need to know the side lengths. We need to know the ratio of the side lengths. And what you're going to notice is when we take the ratio of the side lengths, all the x's cancel. So that we'll know the ratios. We won't know the actual side lengths. Okay, so let's say the sine of 45 degrees. Well, I got two 45-degree angles. How about I'm going to say this is my angle that I'm dealing with, right? So the sine should be the opposite over the hypotenuse, which is going to be x divided by x root 2. Well, that's 1 over the square root of 2. The x's cancel. And then rationalize the denominator. What'd you get? The square root of 2 over 2. Okay, cosine. Well, it's going to be the same thing, right? Because the x's are the same. So x, the adjacent is x. The hypotenuse is x root 2. So x over x root 2, which is the square root of 2 over 2. And the tangent. What's the tangent of 45 degrees? 1, x over x. Okay, now we do our reciprocal functions, right? This cosecant is the flip of the sine. Okay, well, before we rationalize the denominator on the sine, it was 1 over the square root of 2. So what's the flip of 1 over the square root of 2? The square root of 2. And for that reason, the secant has to be the same thing. And the cotangent of 45 degrees should be the flip of the tangent, so that is 1. Good. Okay. So then remember 30, 60, 90. Now, when you learn the formulas, I'm not sure if they used x's or maybe they used n. I've seen it done both ways. It doesn't really matter, but you know, in the 30, 60, 90 triangle, remember, the smallest side is across from the smallest angle. So across from the 30 degrees, the smallest side is x, right? The largest side is across from the largest angle. So across from 90 degrees is 2x. And across from the 60 degrees is x times the square root of 3. Right? Square root of 3, I think, is like 1.7-ish. So it's in between 1 and 2. So that makes that the middle length of the side. So now we can do all those same, let's find the sine and cosine and the 6 trig functions for these 30 and 60 degree angles. The sine of 30 degrees would be the opposite x over the hypotenuse 2x. Which is 1/2. X over 2x. How do you do what? This is really turning into a problem. Let me try this. X over 2x. Right? The x's cancel. Right? That's a common factor. So it's 1/2. Right? If I do the cosine now, it'll be x root 3 over 2x. Which is the square root of 3 over 2. And the tangent of 30 degrees should be the opposite x over the adjacent x root 3. Which is 1 over the square root of 3. I don't know what's going on with this. It's killing me. Which is 1 over the square root of 3. But we have to rationalize that. Square root of 3 over 3. Okay, now we got to do the flips for the cosecant and the secant and the cotangent. The flip of 1/2 is 2. The flip of root 3 over 2 is 2 over root 3. What's that? When you have a common factor, there was no x's. Root 3 over 2. So we already canceled the x's. X cancels x. Did you see that? So, and now we have to rationalize denominator. 2 over root 3 becomes 2 root 3 over 3. What's the cotangent? Just root 3, right? If you go back to this one right here, right? 1 over the square root of 3, and then flip that to get the square root of 3. Okay, now let's try the sine and the 60 degrees, right? The sine of 60 degrees means now we're using this to define what's opposite and what's adjacent, right? The sine of 60 degrees is x root 3 over 2x which is the square root of 3 over 2. Okay, and the sine of 60 degrees now will be x over 2x, which is 1/2. So you notice anything there? The sine of 30 degrees is the cosine of 60 degrees. The cosine of 30 degrees is the sine of 60 degrees, right? And it's not just those two particular values. Anytime you've got two complementary angles in the triangle, the sine of one of those angles equals the cosine of the other. It's because that's just how you define the angles. It'll always work that way. The tangent then, you know, again, we can say the tangent is x root 3 over x, which is going to be the square root of 3. And now for the cosecant and the secant and the tangent, I mean, we're going to flip or pretty much just take it from up here. The cosecant of 60 degrees should be the secant of 30 degrees. 2 times the square root of 3 over 3. And the secant is 2. And the cotangent is root 3 over 3. Now this is what we're doing right now, where we're taking what you already knew about trigonometry and what you kind of already knew about the special right triangles and put it together. You didn't do that in geometry, but this has a lot to do with what we do next and what most students remember about the basics of trigonometry. I mean, we'll see these things coming up a lot in the next lesson. Okay, so find the value of x. We've got a missing side in a right triangle. And we notice that the angle that we know is actually from the special right triangle. It's 30 degrees. So first let's set up the equation, and then we'll be able to actually use what we already know about the special right triangles to solve this. We won't even need a calculator. Okay, what trig function are we going to use here? You know, based on where that angle is, what are the 2 out of the 3 sides that you know here, or that are labeled? Opposite, adjacent, hypotenuse. You know, The x is the adjacent side to that. The 8 is the hypotenuse. So which trig function will we use that uses adjacent hypotenuse? Cosine. So you got first you got to determine what's the trig function that I'm going to use. So then you've got cosine of 30 degrees equals x over 8. But we know what the cosine of 30 degrees is. We did that on the last slide. Or actually, yeah, on the last slide. What is the cosine of 30 degrees? Cube 3. The square root of 3 over 2, right? So we can replace the cosine of 30 degrees with the square root of 3 over 2. And that equals x over 8. Solve for x. How do I solve for x? How do you isolate x? Just look at the x divided by 8. What do you do to isolate x? Multiply times 8, right? So I multiply both sides times 8. Now, can we simplify that? 2 goes into 8 4 times, right? So that's 4 times the square root of 3. Yes? Which one? No, because in this case, that x doesn't represent the x in the formula. It's just labeling that side as a side we don't know. It's not saying that that's the x in our formula. Because where would the x in our formula have been? It would have actually been over here, across from the 30 degrees. That's where our formula had an x. I mean, if it helps, like if you don't want to use x, then call it y. Call it something different. It wasn't intended to be like that x. I mean, the truth is that we know if that side is 8, we know this one is 4, and then using your special, right triangles, not even resorting to trigonometry, then this side must be 4 times the square root of 3. Okay, so try this one. Try to find the side A and side B and angle A. So, I mean, the math in this one it's pretty much the same. I mean, the other angle had to be 45, right? There really wasn't much to find there. So you could use either one of those 45s and then use either sine or cosine. It wouldn't matter. You'd get the same thing. I said sine of 45 is b over 5. So clearly I was using this angle here. And the sine was b over 5. But I know from our previous slide, the sine of 45 is root 2 over 2. Then solve for b, multiply times 5. Now, do I need to go through the same process to find the a? No, because I know that these two are equal. So once I found one of them, I knew the other one too. So, seems like I got this goofed up. Okay, no, it's okay. The standard labeling of right triangles. We kind of saw it in the last picture, but just to be clear, because sometimes they'll like not even draw the triangle for you. They're just going to give you the values of A, B, and C, capital A, capital B, capital C, and you don't really know what they're talking about. So in any triangle, really, but we're doing it for a right triangle here. We use the capital letters A, B, and C to represent the angles. We use the lowercase letters A, B, and C to represent the sides. Right? The capital letters are across from the lowercase letters. So across from the right angle is always C, right? So the hypotenuse is always lowercase c. Now, which one of the other two angles you label as A and B, it doesn't matter. But you're going to go across from the capital B to find lowercase b, and across from capital A to find lowercase a. That's just a standard convention of the way you do this. Okay. Ready, Michelle? All right. Now, if they say solve a triangle, what it means is find all the missing sides and angles. That's what it means to solve a triangle. Now, look at the triangle that we've got here. What's different about it than the other two that we just did? Yeah, it's not one of these 30, 60, 90 or 45, 45, 90, which means we're going to have to use a calculator. Okay. So, first let's set up the equation that we're going to solve. Let's see, our angle is here, right? And the two sides that we have to pick, we got more than one side to solve for, right? So what would be the easiest thing to solve for first? We have the other angle. What's the other angle? 62, right? This should just be 90 minus, so 62. Okay, now we need to use a trig function to find A or C. Which one would you like to try first? The A? Which trig function? What's that? Let's see. If we're going to solve for angle A, we've got to use the one side that we know, right? So if these are the two sides you're going to use, what's the trig function? It's tangent, right? So I'm going to have tangent of 28 equals A over 15. Solve for A. Right, you're going to multiply both sides by 15. Make sure you don't multiply 28 times 15. You're multiplying by 15 in front of the tangent. Okay. Now, 15 tan 28. Bring up your calculator. $15 tan 28. $7.9756. Did anybody get something different than that? If you did it, you could. I mean, clear the memory and try it again. Yeah, what'd you get? Okay, so Gray tried it and he got -4, which is not right. Okay, but notice the mode key right here. If you click on the mode key, the third line down is where you've got to set the degree to measure in degrees. There's actually another way to measure angles, and that's in radian measure. That's what we do next class. And usually the default on the calculator is radian measure. So if you get a funny answer, you might want to check the mode that you're in. So if you get it set to degrees, you should get this, what did I have, second quit? 7.97, that's going to round to 8, right? Okay, how am I going to find the C? Cosine, okay, if I'm going to use this 28 degrees and it's 15, then it'll be cosine of 28 degrees equals 15 over C. Solve for C. C equals 15 divided by the cosine of 28. So remember, if you get something like where the variable's in the denominator, that C is in the denominator, in the end, it's just like you switch the positions of the C and the cosine of 28. C equals 15 over cosine 28. 15 divided by cosine of 28. 16.99, 17. So there, we solved for the missing sides, we filled in the missing angle, done. So try this one. Same kind of process. Right, so the angle was 58 degrees. And then at that point, you've got many options for how you're going to solve this. I mean, I actually used the 58 degree angle and said the tangent of 58 is b over 10, because then I could keep the variable out of the denominator. So I got 16. It rounded to 16. And then I used the sine of 32 is 10 over c. And then c is 10 over the sine of 32, 18.9. Any questions on that? Easy? Okay. So word problems. Anybody been to the Grand Canyon? I heard somebody on TV going on and on about the Grand Canyon over the weekend. And I've been there like once. I was a kid. Haven't been back. But it was one of those things, I didn't really think much about the Grand Canyon before I got there. But when you stand there, when you're like right next to it, it's just like unbelievable. I mean, you just can't even imagine something looking so beautiful from standing on the side. And that's what this person was going on and on about on the, I hadn't remembered that, but it's just unbelievable. Just go to the Grand Canyon. Right. So while standing at Yavapai Point near the Grand Canyon, you measure an angle of 90 degrees between Powell Point and Woodforest Point. I've already labeled it on the diagram. So what does that mean? It means we can use right triangle trigonometry. Okay. You then walk to Powell Point and measure an angle of 76 degrees between Yavapai Point and Woodforest. That would be right. Let me get a yellow, a good yellow. That would be right here, 70. Let me get a thicker line. So that's 76. Okay, the distance between Yavapai Point and Powell Point is 2 miles. Okay, so that distance here is 2. Find the distance between Yavapai Point, which is here, and Woodforest, which is here. So basically, we're trying to find this side. So here's our angle, 76 degrees. We know this 2, that's an adjacent side, and we're trying to find x, that's an opposite side. What trig function? Tangent, right? So we got to use the tangent of 76 equals x over 2. So the distance is 2 times the tangent of 76 degrees. Two times the tangent of 76. Looks like 8 miles. Okay. Now, a lot of the word problems you get in trigonometry, especially the right triangle trigonometry, they're going to use these expressions here. Angle of elevation, angle of depression. Right? The angle of elevation is the angle that you're looking up from a horizontal line. The angle of depression is the angle that you're looking down from a horizontal line. But definitely both of them, one side of the angle is a horizontal line. So when you get this kind of a problem, there may not be a picture. You're going to have to draw your own picture and label the angles correctly. right? If it says it's an angle of elevation, and you got to make sure one side is the horizontal line, it goes up from there. So angle of elevation, angle of depression. Problem. A parasailer is attached to a boat with a rope 300 feet long. The angle of elevation from the boat to the parasailer is 48 degrees. Right? Estimate the parasailer's height above the boat. Okay, so where am I going to put the 48 degrees? Right down here, right? 48 degrees. I'm sorry that this doesn't look good, but where do I put the 300? It's this side here, right? And what am I trying to find? The height above the boat, right? So I'll call that H. So I wish that drew that better. 48 degrees. Okay, which trig function am I going to use to find H? Sine, right? Opposite over hypotenuse is sine. So I've got to go sine of 48 is H over 300. So H equals 300 sine 48. Okay, let me do that. $222.9. You like my picture? Yeah, well, it's a lot of work for that. Okay. So try this one. Similar problem, but not quite the same. A different parasailer is 200 feet above the boat. So now we know how high he is above the boat. The angle of elevation is 38 degrees. Find the length of the rope. How many got it? Fair number? Okay. I mean, like I said, a lot of times you're not going to get a picture. You have to visualize the picture. Know what you're trying to find. Okay. Now, my guess is that when you did this in geometry, you learned in the same lesson about inverse functions, about how to find missing angles. But in this book, they separate that out, right? Between 13.1, which we just did, and 13.4, they talk about inverse. But inverse trig functions, there's a whole lot to those that we're not doing now. We're really only interested in, okay, how do you use an inverse trig function to find a missing angle? Okay. So up till now, we always knew the angle. We didn't know a side. We either already knew the angle, like in the 30, 60, 90 or 45, 45, 90, or we didn't care, right? We were just being asked for what's the sine of theta. We weren't asked for the theta. What's the sine of theta? That's a ratio of sides. Okay, in order to find missing angles, you need trig functions. Or sorry, inverse trig functions. Sine inverse, cosine inverse, and tan inverse. Right? On your calculator, they're right above the sine, the cosine, and the tangent. You have to use the second key to get at the inverse functions. Now, remember about inverses, right? A function and its inverse point in opposite directions. So, for example, if f of 1 equals 2, then f inverse of 2 equals 1, right? They do exactly the opposite of each other, okay? And the composition of a function and its inverse, f minus 1 of f, cancel each other out. Right? And that's why we use them. When you can't isolate a variable by doing algebra stuff, you need an inverse function. So remember those two things. So the cosine inverse of the square root of 3 over 2. Where did we see the square root of 3 over 2? That should be familiar. It was what? It was the cosine of 30 degrees, right? So the cosine of 30 degrees equals the square root of 3 over 2. Okay, so what's the cosine inverse of the square root of 3 over 2? $30 degrees. Right? That's the inverse. How about the sine inverse of 2? The sine inverse of 2, did the sine ever equal 2? It equaled a half, right? And the cosecant equaled 2, but the sine never equaled 2. Use your calculator, find the sine inverse of 2. See what you got. You get an error, right? Okay, there's a reason for that. Remember, the sine of an angle is the opposite over the hypotenuse, right? It's a ratio of sides, opposite over hypotenuse. Which is going to be bigger, opposite or hypotenuse? The hypotenuse is always the biggest side in a right triangle, so this number has to be less than 1. So there's no way you can find the sine inverse of 2 because there's no way to take the sine of, or there's nothing that you can find, no angle that has a value of the sine of greater than 1. In fact, what we learned in the next lesson, it can equal 1, but it can't be greater than 1. If we're just doing right triangle trigonometry, we don't even see how it equals 1, but we definitely know it has to be less than 1. So this one is error, does not exist. Can't take the sine or the sine inverse or the cosine inverse of a number bigger than 1. Okay, try these two. Let's see. Now we're up here. Okay, I think I just missed that one. That's okay. Okay, what is the measure of this missing angle? So now we're just using this like you used it in geometry. I mean, like we've really already used it to find missing sides. What's the function we're going to use to find theta in this problem? Okay, look at, here's the angle. This side is the adjacent. This side is the hypotenuse. That means it's cosine, right? So cosine of theta equals 6 over 11. How do you solve for the theta when it's actually inside of a function? Okay, you can't divide by COS. That doesn't work. Okay, what you can do is you could take the cosine inverse of both sides, right? So the cosine inverse of the cosine, take it of both sides, you know, what do you get when you take the cosine inverse of the cosine? What did we say? F minus 1 of F is? They cancel each other out. You just get the thing that's inside the function. You done? Just put it right there. And then the cosine inverse, you can put that in the calculator. Right? What is the cosine inverse of 6 over 11? $56.9. Okay, try this one. That's your U try. 1.8. And you know, you don't have to show taking the sine inverse of both sides, but that's where it comes from. That's something that when you did this in geometry, they just said, just do this. So you had no reason to understand why it worked. We do now because we know something about inverse functions. Okay. Theoretically. Okay, one more, because you got to do a real world problem. A monster truck drives off a ramp in order to jump over a row of cars. The ramp has a height of 8 feet and a horizontal length of 20 feet. What is the angle of elevation of the ramp? So I got to label this thing here. Okay, where do I label the 8 feet? On the right, says the height. Where do I label the 20 feet? It says it's the horizontal length, so it's got to be there. Okay, where do I label the angle? It says the angle of elevation. No, yeah, well, I got to label it. Bottom left corner, so I'm going to call that x degrees. Okay, which trig function can I use to find the x? Tangent, opposite and adjacent. So this is the tangent. The tangent of x equals 8 over 20. So x equals the tan inverse of 8 over 20, which is what? Say again? 21.8. Okay, that's it. That was a long one. There's the homework.